Thanks for the invitation. It is my pleasure to talk about two systems that we have developed in recent years. One is multi-domain model checker, PAT. The other is explainable and verifiable machine learning system called Silas. In recent study, software failures are estimated to have cost over $1 trillion worldwide each year. A recent software design error in the Boeing 737 MAX 8 maneuvering characteristic augmentation system called Marcus cost 346 lives, billions of dollars in potential sales, and also the trust in the safety critical software of a Boeing company's reputation. Software are becoming larger than ever, more complicated, and their development involves more engineers and developers. All of this lead to more bugs, more unexpected outcomes, and more unplanned corner cases. Systems are increasingly connected, and more network devices interacting via complicated protocols with 5G networks, sensors, mobile phones, IoT devices, etc. There are many more complicated interactions possible. We are building systems that are more optimized for the improved efficiency. However, the more optimized the system, the easier it is for small change to disrupt the whole system. As the systems grow more complicated, they are also becoming harder to understand and less transparent. This is particularly a problem with the modern systems that are depend on machine learning and AI. They often perform well, but it is very hard to understand why they are taking the actions they are taking. We are seeing more and more attacks to our major distributed systems as more and more value is placed on those systems. So sound software engineering techniques like a formal analysis, formal method is even more needed. The history of formal analysis can be traced down to an early paper by Alan Turing called Checking Large Routine in 1949. The Turing Award winner Tony Hall has also invented an event-based calculus called communicating sequential process, which provides an elegant theory for modeling concurrency and communication. Our modeling language are based on this particular calculus. On the verification side, 3 researchers also won Turing Award in inventing the model checking techniques. One of them, Adam Clerk from CMU, has won also the Franklin Bowers Award. Model checking has been widely used by major industries such as Intel and Microsoft. For example, the Intel i7 core execution cluster is completely verified by the in-house model checker from Intel. Microsoft Driver Verifier is also based on model checking techniques, has been in production since Windows 7. In our research work, our modeling language is based on whole CSP. Our model checking algorithms is based on Adam Clerk's work. So I'm very grateful for Tony Hall and Adam Clerk in the past few years who visited my group multiple times, offer many valuable advice and collaboration in various projects. So the work we have done in the last 12 years, I have jointly with my 2 former PhD students, Sun Jun and Liu Yang, where Jun has joined the SMU and Liu Yang has joined the NTU as a tenured professors. We have a continual collaboration on the PAT system. PAT is extensible reasoning systems for system specification, simulation, and verification. It has 2 verification engines. One is based on explicit model checking. One is based on symbolic binary decision diagrams. PAD has attracted thousands of registered users from hundreds of organizations. Particularly, the commercial version PAD in Japan was selling quite well to some major companies. PAD has also applied to event planning and the scheduling problem. So a student used PAD actually has won the EXE score competition years ago. So in the recent years, PAD is used in a number of research projects. Most of them are related to cybersecurity. Today, I will focus on two recent projects. One is on trusted autonomy, which is funded by Australian Defense Department. The other is apply probabilistic model checking module in PAD for sports analytics. There are many defense hardware autonomous systems developed by various countries, but the key challenge is to develop a trusted decision-making software that controls those autonomous systems. So this project is funded by Australian Defense Department. It uses PAD to make a goal selection and path planning for deep sea autonomous system called Ray. The model checking based planning and the goal reasoning framework is quite generic, that it is not only designed for the deep sea Ray, but also can be applied to many other autonomous systems. Here's the example. The autonomous ground vehicle start at a position H and aims to visit positions like A, B, C, D, E, and recover, recharge the battery at position R. Given its partial environment knowledge, PAD API service automatically computes and optimizes the travel routes initially. However, during the real-time execution, after visit position A, its computer vision detects the enemy blocked the original travel route from A to B. So PAD can recalculate another travel routes to visit the position C first, then B, D, E, R. However, there is not enough battery for this new traveling route. So in this situation, PAD will select a subset of goals that maximize the rewards without running out of the battery. Another interesting project is to apply probabilistic model checking for decision making. Traditional probabilistic model checking application domain is to calculate the reliability of overall safety critical systems in terms of reliability of system components. For example, the overall reliability of aircraft can be derived from the reliability of the aircraft components and the sensors. Well, we're the first one to apply probabilistic model checking for sports analytics. Data and the statistics has been used in early days in sports analytics. You may remember the Brad Pitt movie Moneyball. It is a typical example. Another interesting example is during 2006 World Cup quarterfinal between Germany and Argentina. Just before the penalty shootout, the German goalkeeper read a note which contains the direction of each Argentina's player likely to shoot their penalty. Maradona, top corner. Messi, left, right, corner. So based on this collecting information, the Germany beat Argentina 4-2 in the penalty shootout. Another more recent, a great victory in 2014 when Germany won 7-1 against the host Brazil. Guess which company takes the credit? Maybe give a little bit more hint. Which IT company taking the credit? Maybe more hint. Which German IT company taking the credit? Now you probably can guess. Well, it is SAP. So SAP uses RFID sensors, data visualization, monitoring, scheduling the player for the best performance. So during the semifinal, German got the best team, well rested. Well, Brazilian probably already injured. There's a few key players by the time in the semifinal. That was probably the reason that Germany had a big win over Brazilian team. In tennis, match fixing actually is a major problem because only take one player to decide I'm going to lose tomorrow. However, some kind of a data analytics on match fixing prediction is quite wrong. We actually have proof that the certain analysis, even published in BBC and CNN News, was actually having mistakes. Of course, we're using probabilistic model checking to prove that. So to perform that, we use PAD probabilistic model checking module and also develop and generate Markov decision models for each professional player. We basically develop the right-hand player, the rest just automatically generated based on the historical data. So probabilistic model checking support Markov decision process model and can calculate maximum and minimum winning chance between two players based on historical data. Let's take a Federer Nadal. Because Federer versus Nadal is one of the greatest rivalry in tennis history. Here is the example that we perform at the just before the 2017, we had this analysis. Around that time, Federer is widely regarded as the best player in history with 17 Grand Slams, where Nadal only have 14. Federer has a 300 weeks #1, where Nadal is about 100. Federer also have a 6 ATP year-end final. That's the top 8 players play against each other at the end of the year. Federer won 6 record times. Nadal is still 0. However, another key data is that contradict to those key factors is that the head-to-head, when Federer meet Nadal, this is before 2017, is Federer only has about 30% winning chance. That's only won 10 out of 33 matches. Nadal won 23 times, 70% winning chance. So the question is why? And also from analytics strategy point of view, how we can help Federer to beat Nadal. So that's really the kind of a key question. So we talk about the strategy analytics. Right? If you know a bit of tennis, you probably notice that Nadal's one common use strategy by Nadal is with a very high percentage is running around using his powerful forehand topspin to attack Federer's backhand, which has a relatively low percentage of consistency. Now the question is, what is the minimum improvement on Federer's backhand so that Federer can beat Nadal? This is a kind of a sensitivity analysis in probabilistic model. To do that, we need to take a sports data and develop various models. So we published the first paper in the 2015. We basically declare that tennis strategy is Markov decision process. Here is a simple example. If you start with the first serve and the first serve T into this area, and the return player return backhand cross court, and then the first player will also play backhand cross court, another backhand cross court. That's usually it's just like attack each other backhand. And after number of exchange, this player make mistake. That's the end of one of the rally. So each distribution with a probability in terms of average based on historical data. we got this Markov decision process model. We have developed many different MDP models. One of my favorite model is based on 8 locations. For example, Federer is on top, Nadal is at the bottom. There's 8 locations, number of shared variables. So whose turn to serve to start the game first, we don't know. Federer starts to score from 0. Nadal also start from 0. Who win the game, we don't know. It's because that's what we're going to predict. The ball is initially at the location 9. Maybe someone holding the ball ready to serve. The first serve is decided by a non-deterministic choice, which triggered by the event toss a coin. And whoever won the coin will start the first serve. So it could be either Federer serve or Nadal serve. In tennis, there are 3 basic directional serving strategy. One is Y serve, serving this area. Another serve is around the T area. The third strategy will directly to the player's body to surprise him. For each serve strategy, there is a probability of consistency in terms of in and out. So there's a 6 probability distribution. For example, based on past few years, here's a Federer's first serve distribution. Federer spent about 23% serving T area. If he versus Nadal, that will trigger Nadal's forehand because Nadal is left hand. Federer making about 15% mistake when he's serving the T direction, which will trigger Federer's second serve. Federer majority serve actually serving Y towards Nadal's backhand. That was kind of right strategy. Federer making about 11% mistake, which will trigger Federer's second serve. Federer surprised Nadal with 14% serving to the body, and that will trigger either a non-deterministically Nadal's either forehand return or backhand return. So Nadal needs jumping around, be able to get away from the ball towards his body. Federer only make about 7% mistake when he's serving to the body. Now, the second serve distribution, when Federer make a mistake in the first serve, is quite different. As you notice, Federer only spent 15% serving to the T direction because that trigger Nadal's forehand. Second serve usually slow. Nadal will smash him with the big forehand. So Federer tried to avoid that. Of course, Federer's mistake on the second serve to the T is much less. It only makes about 3% mistake because if you make that mistake, you lose a point. It's called double fault in tennis. So the Nadal will get a point, and here's a piece of algorithm to calculate who's going to serve next. And again, there's a 6 probability distribution. I'm not listing all of them. I just give you some idea. Now you got what this MDP model is. You got this probability distribution and the non-deterministic choice is a very classic Markov decision process model. Without non-deterministic choice, we got a Markov chain model. You may ask what the data looks like, right, to generate those probability distribution automatically. Well, here's one of the data between Federer and Andy Murray. So the detail of the data from tennisabstract.com, which collected more than 5,000 or 6,000 matches, something like this. This is first serve down the T, fault, second serve to the body, backhand return down the line. So we're taking this data, automatically generate all the probability distributor in the past few years in average. So once you have this, you can have quite a bit of interesting analysis based on different situation, different pressure point and the score, and what is likely the probability distribution when they're serving directions. So that's already give us some players some pre-knowledge, some kind of advantage. Of course, you may start thinking maybe this approach can be applied to online betting and making money straight away. Yes, indeed. In Singapore, well, it is not allowed to do online betting except that Singapore government betting site. So here is just a simulation using our model to play against one of the large online betting company, that UK365.com, and show that we are actually making 23% profit. Well, this is not what I'm really interested. I'm more interested in the strategy analysis, helping a player to have a better chance to win the match. So I think it's time let's do a live demo. Okay, so this is the model between Federer and Nadal. As I said earlier, the first serve had this 23 distribution to the T, 15% mistake, and the second serve had this probability distribution. And we model every actions, backhand cross court, backhand down the line, forehand cross court, and so on. Given this model, Federer was an Nadal based past few years, you can calculate Federer winning chance. As I said earlier, the Markov decision process will calculating the minimum and maximum winning chance for Federer against Nadal. So the result, as you can see, the minimum is about 46%, maximum is 47%, both below 50%. What that means is mathematically proved or formally verified that Federer actually losing to Nadal, both below 50% chance. So the question is, how we can help Federer to beat Nadal, to achieve, both perhaps over 50% with very minimum improvement. Now let's look at Federer's backhand. Federer single backhand, not as stable as double backhand. And it was quite alarming that Federer making about, based on historical data, Federer making is about 18% mistake when Nadal hitting too deep into his backhand. The question is, can we improve this 18% with a very minimum improvement? Let's say 2%. So, okay, let's do a real time. So we're gonna reduce 18% to 16. And put that 2%. So what was the decision making? To where? Cross court or down the line? So if you know a bit about tennis, you should recommend down the line, because that's backhand, for Federer backhand down the line will hitting towards Nadal's backhand, right? Because Nadal's strength is his forehand top spin. So we're going to add that 2% into this 18%, update that 18 to 20. Yeah. Now we didn't change any other 300, 400 probability distribution, serving the same, forehand the same, volley the same, everything else the same. Now let's have a look. What's the Federer winning chance now? This is like sensitivity analysis. Remember before the data, before we did this minimum improvement, the Federer chance was 46, 47%, both below 50%. Now, the minimum is over 50%. The maximum is 51%. Now Federer can beat Nadal. Cool. So actually, I give the same demo at the end of year 2016 in with the two many tennis coach in Australia. One of them, no Federer, say we'll pass a message on. Well, guess what? Since the end of 2016, when I present that to those coaches, the message passed on. Federer actually in 2017 beat Nadal every single time. Only in Roland Garros, one was Nadal favorite. In 2019, Federer lost to Nadal. So Federer is having about 6-1 head-to-head since 2017. What do you think? Federer definitely owns some money to me, He hasn't paid yet. So what I'm going to do, I'm going to use a low to teach Federer lesson. So I'm going to use a low player, ranked player, John Millman. He's a good friend. Also live in Brisbane. Actually, a hitting partner with my son. He's a mentor to a top junior player in Australia. John Millman was only ranking 42 in the world at the time when he met Federer in 2018 US Open. So here's my communication, my mobile phone, my business card, communicating with John Millman, sending all the statistical probability profile Federer to say where to serve to get a short ball and where is unfolds error likely and so on. So John's very appreciative. And actually won that match against Federer, against all the odds. Because the betting odds for John to win at that time, you put $1 in. If Federer win, you only get an extra 3 cents. But if you put $1 in, if John Millman win, you get $19. So this just shows that we can actually helping players to optimize their chances to win. I'm not going to take the whole credit. John is hardworking and played extremely well during that day against Federer. They are good friends too. So but definitely we're happy to play a small part by providing those probabilistic analysis to optimize the strategy of John Millman. We also have other kind of analysis, also based on different kind of matches to calculating what's the back action to improve, what's in general the right-hand player or left-hand player. And another interesting project, we're also looking to apply this approach to more than 2-player game, right? We also apply the same approach to tennis, table tennis, badminton. Basically 2-player games is Markov decision process. But it will be interesting to apply this approach to multiple players, more than 2 players, and also combining probabilistic model checking with machine learning. Okay, here is a simplified poker game to get this idea across. Since it is probabilistic in nature, also requires learning, we think it is good, case study to demonstrate how model checking and machine learning can be integrated together, where input from machine learning can be fed into the pad model checking systems, where the result can be used to generate an action back to the controller. This iterative process lets agent to approximate its opponent's strategy and helping to play the game better gradually. So the game consists of 4 players, 5 cards, 10 to ace, where 10 has the lowest value, where ace has the highest value. In each round, every player has to put down a chip. Each player can guess a card. Then it is their turn to take action. They can choose whether to bid or not to bid. The game ends when all player doesn't bid, or when some player has bid, and then every player has responded to that bid. So let's go through an illustration to help you to understand this game. So today I'm not just teaching you how to play tennis, but I'm also teaching you how to play a poker game. So the start is that everyone put down a dollar on the table. Each player is dealt with a card. We can see our card. The opponent's card, we cannot see it. There is a 5th card hidden. Opponent 1 turn to make a decision whether he's going to bet, put the $2 in. So the opponent 1 decide not to bet the second one. We also have a queen, which is not very high card. We also give a pass. We not put that $2 in. Opponent 2 look at their card. Wow, I've got a good hand. Maybe I put a $2 in to challenge everyone. So everyone need a response. Opponent 3 perhaps pretty conservative. I don't have high cards. I'm going to lose this dollar. Opponent 1 thinking, opponent 2, you're probably bluffing. You may not have the highest card. So I'm faced the challenge, put the second dollar in. Usually we will give a pass, right? And just make it more interesting. We're thinking about maybe both players are bluffing. The hidden card here, it's ace is here. This guy got the kings, is pretty conservative. Those two just bluffing. So thinking, okay, let's make it interesting. Put the second dollar in. And then the 3-player challenge each other will show the cards. Guess what? The usual case, opponent 2 indeed have a highest card and won all the money for this round. So we basically using probabilistic model checking to make decisions, and also combines machine learning to observing each player's behavior. Are they bluffing or conservative? Are they change from bluffing to conservative, or from conservative to bluffing? The more hands we play, we have much better chance winning all. So those are the kind of the data experiments we have conducted. So the general idea is that whenever you have a big sports data, military data, we can combine with probabilistic reasoning with decision making and the machine learning to make decisions, either certify a system is correct or make some kind of planning a decision. So what is interesting is combining a formal verification techniques with machine learning. From that kind of direction, we also has another project which looking at how to combine machine learning with formal automatic reasoning techniques. So that's come to the second topic, which is the Silas. Silas is a tool that combines machine learning with formal reasoning. It is also a high-performance system. Silas has 2 key features. One is Komodo Insight. It's apply automatic reasoning techniques to provide insight on model prediction. The second feature is Komodo Audit, which is using formal verification techniques to automatically prove that the prediction conforms with the user's specification. And it's high performance, it's also accurate. The Silas architecture consists of machine learning module, which perform learning and the meta learning tasks. This is what everybody else does in the machine learning community. So the new stuff is that on top of analysis of data, we also aim to analyze the predictive model itself. To do so, we reason about the logical representation of the model using state-of-the-art SMT solver like Z3. This part also solves the problem of understanding the predictive models. The model audit feature is concerned with the formally verifying that the model is correct with respect to user specification, to ensure that the user specification are respected in the model. Silas is about 6 times faster than the H2O, which is a very popular white box open machine learning systems. When building a similar size model with a similar predictive performance on the same training test data. So this benchmark is generated by 1 million US flight data sets, just to predict which flight are likely to be late. How to achieve this? It's actually achieved by many low-level code optimizations. Silas also very memory efficient compared to other rivalry tools. Silas also performed quite well against many systems in public data sets and benchmarks. Particularly with large volume data, Silas performed remarkably well. So that's pretty much what I like to talk today. We looking for collaborators. Hopefully, if you're interested, drop us an email. Whatever, if you have questions, you can ask now. Thank you.
Thank you, Prof. Thank you, Prof, for the really interesting talk. And it's a very, especially the tennis example was very interesting. And it was very interesting for me. So we have a question ready from Ananya. Is Silas a platform that embeds causal inferencing into ML tasks? Prof, I think you're...
Okay. Silas mainly embedded SMT solver, like say 3, to give a logical interpretation. Currently it was doesn't have a causal inference.
Yeah, I think that. Thank you. So now we have another question as well from Kiran that thanks for the great talk. It was very interesting to see formal methods applied to less rigorous domains such as sports analytics, where I wouldn't have expected the typical benefits it provides to be useful. Are there any other domains you think formal methods could be applied to in the future, for example, but are underutilized for the moment?
Yeah, indeed, sports analytics is a surprise one, because usual application domain for methods always safety, security, critical systems, and a particular probabilistic model checking is used for calculating the reliability of a safety critical system like aircraft. If you know the wings reliability and all the sensor reliability, you can calculate the aircraft reliability. So that kind of idea is applied if you're thinking of reliability of a player in terms of the consistency of all his components, forehand, backhand, volley, and different kind of tactics. So you can calculate the overall reliability of this player in terms of probability. So the idea can be applied in the very unusual application domain. So sports analytics is one. We also look into environmental predictions. If you're changing a certain resources, allocate government resources, a certain policy, to what's the impact to the environmental changes. So there is a project with the French collaborators looking at environmental changes using probabilistic model checking. And I guess there's also financial thinking is predictions in the financial side. And should I buy this company 15% share, or I should buy it 30% share? Temasek should make a reasonable kind of a decision whether that can be probabilistic model check against all the decision of their major board members. Everyone give a certain input, perhaps based on the company's profile, we can have a robust confirmation checking in terms of the financial decision making. So there are a number of other kind of unusual formal method can be applied. Good question.
That's actually interesting. Especially, the environment prediction is also, that. Thank you. So now we have another question too. What does the explainable machine learning mean here? How do you make the machine learning model explainable by using probabilistic analysis?
Right. So this is a Silas work, is that so if you get an insurance, right, you try to apply insurance, and sometimes you just get a rejection, or get a housing loan, and you may get approval or get a rejection. It would be nice the customer deserve explanation why my application is not successful. So the machine learning model used by Silas can basically calculate the weight of certain features going to carry a significant of impact in the prediction model, explaining certain reason why certain thing was not get approved, just as, for example, in the insurance case. So that's the explainability provided by the Silas machine learning system.
Right. Okay, thank you. There's a follow-up question on the earlier question by Karen too. Thanks for the answer. As a follow-up, with respect to the sports analytics, what advantages versus disadvantages do these formal approaches have versus more standard approaches such as machine learning? Yeah,
again, very important question. We actually tried both. What Silas can predict, sometime Silas actually apply to the tennis match, also against the the betting side. But that was conducted in Australia. So in Singapore is illegal. So in Australia, what conducted machine learning mainly is competing against other advanced algorithms and the strategies in this open betting market against each other, basically. So what Silas focus on mainly just performing against those systems. It's just end of result, making money or losing a little bit of money, or majority making big money. What a probabilistic model checking, which I'm more interested in, is that as you know, I'm also a coach for at least for my kids. I like to give a little bit of feedback using the system. For example, I can tell my son, hey, today you lost your match. Guess what? You have 5 double faults. If you cut down your double faults from 5 to 3, guess what? You win the match today. That's how important. Go back to practice serve. So that's kind of a feedback can be gathered from this probabilistic model checking through this sensitivity analysis. Like I demonstrated, through if Federer improves his backhand only 2%. 2% means 1 in every 50 balls don't hit out and hit that ball down the line. So that's the decision making rather than cross court. The impact of that will improve Federer overall winning chance against Nadal, roughly more than over 3%. So that's a kind of the unique feature of this sensitivity analysis offered by probabilistic model checking is also give a kind of explainability. I just find it more interesting from the coach point of view. Of course, this is also money making. We negotiating agreement with Tennis Australia. They want us our system only used for Australian players. But we like to open up for other players. Right? So I think Federer has a lot of money. He should pay me more if he uses my system. That's a different side of the story.
Yeah. Thank you. Thanks for the answer. So we have another question from Ernest. Now, can PAD be used to verify cryptographic protocols like the probability of an attacker to break encryption?
Yeah, I mean, formal method has been used for many security protocol verification. It's very rich literature. There are many tools. PAD is not the only one can be used. There are many very specific formal method tools based on applied pi calculus, which can be also very efficient to verify many different kind of security protocols. If you even Google, say, formal verification security protocol, there's a huge number of papers in the cybersecurity literature. Yeah, indeed, I think it's has a lot of potential, but we are not saying PAD is the only one can verify those protocols. There are many other formal tools, analysis tools, in terms of cybersecurity protocol verification.
Hi, Prof. I have a question. So from the example, you showed that there are many of the probability numbers. I'm just curious that how do you collect those data? Or in other words, like how do you guarantee that those probabilistic model actually reflects the real situation?
Again, very good question. The probability parameter is calculated based on tennisaddress.com, which is a community collected data for professional matches. So they have about 5,000 or 6,000 matches by now. And we automatically querying those data, automatically updating each professional player's probability profile, month by month. So that give us a very updated how the players' improvement, how they change their strategies, and so on. But you are right, even those data, because it's community collected, they using mobile apps and pushing certain buttons and creating this file automatically, but it's still manually watching the video by collecting this as a community work. So the data sometimes not very reliable. If they tire, they miss one shot, the Federer and Nadal sequence will be actually switched. So we also have several other algorithms automatically detecting this data error to remove a certain chunk of data from tennisapp.com. So most recently, you probably know one of my PhD student, Jian Kang, working on tennis analytics. He's really looking into like a video analysis. Look at a video, can we from the video and automatically to come up those input like the one manually put it in tennisapp.com, but automatically calculated based on the video analysis by a computer watch the video and then come up those point by point input. So that also actually will improve the reliability of the data, but also opened up the possibility, not just helping to consulting, say, for the professional player, but can also help a U.S. college player, like NCAA player, right? My second son is playing right now in the U.S. College League. So to helping each team to against each other based on the profiles, previous historical data of other rivalries, that will give an advantage to those teams.
I see. Thank you so much.
Thank you. Very good question. Thank you.
Thank you. Thank you, Prof. Sorry. Yeah. Thank you. I think, that seems to be, No, I think if there are more questions in the interest of time, probably we can, if there are any more questions, we can, I think, have the time for one more last question or else, yeah.
Oh, can I ask one more question?
Sure.
So do you see there is opportunity of research that if we model the probability into like an interval kind of a parameterized parameter, do you see any of the challenges of doing that?
There are a number of research work actually rather than a particular fixed parameters. They have give a range of possibilities. And I think that's also can be useful in terms of sports analytics. And also this idea, for example, the 2%, right? I just did a couple simulation. I found the minimum 2% can helping Federer to beat Nadal. But we can actually calculate this 2% by using some of the recent research work called parameter synthesis. That is, if you want to have an overall winning chance over 50%, what is the delta of a particular parameter to synthesize this 2% automatically?
I see.
Non-trivial, but in this particular case, but it is a very interesting recent research work has been focused on this so-called parameter synthesis.
Parameterized, I see. Okay. Yeah. Thank you so much.
Very good question. Thank you.
Thank you, Prof. Actually, I think there are quite a few questions, but so there was another question actually that I mean, it's similar to yours question that how do you convince people to trust your analysis? So
yeah, okay. Firstly, for pattern model checking, even though we have 1 million source code of C# source code, right? Firstly, how reliable the model checker, the source code of a model checker. So we actually eat our own medicine. Their major decision procedure, major algorithm in PAD is also self-model check. We also using Microsoft Spec Shop, which assertion with the pre-post conditions, also like a theme proving stuff. Also prove the C# source code of PAD source code are reliable. So there are a number of effort has been put into to ensure that the source code of PAD itself and also be model checked, be formally reasoned about. Yeah, good question.
Thank you, Prof. I think in the interest of time, we're going to have to, for more questions, I think you can,
But I think that maybe if I misinterpreted the question, for example, when Pat predict the percentage of Federer winning chance, the question was, how do you know that was the real winning percentage, right? Indeed, I think this is a total open question. That's why there's a platform. All the top, mathematicians come up their own system against each other to see who's the best. But what is the benchmark? Usually against the top betting company. If you're making money out of them, your system is more accurate.
Right. I think that's thank you for all the answers in the great talk. I think for more questions, I think you can approach Prof directly, or you could drop him an email later or take it offline. Thank you so much, Prof. I think
thank you very much for the invitation.